man you saw, is going to be our first speaker this evening. So please join me in giving a warm welcome to Abidoye.
Hi. Well, this evening my classmates and I are going to have to ask that you participate in a few experiments that we're going to do throughout the course of the night. So the first one is I'm going to have to ask everyone to get up on their feet. On your feet, Thank you. Now put your drinks down, you're not going to need them. Put your drinks down. Please just put your drinks down. Now raise your arms above your head and flap them around. Flap them around really, really fast. Really fast. Faster. Now put them down. Now put them back up and flap them. Wave them around while you flap. Wave them around while you flap them. Like wave them. You may sit down. Congratulations, you have just irrevocably changed the pattern of the Earth's weather forever. I hope you have. Well, this evening I am here to tell you all you need to know about chaos theory without a math degree. And in case you didn't know before, my name is Oladimeji Abidoye. So what exactly is chaos theory? I mean, is it just really about disorderliness and everything being random? Before we can actually get a really in-depth knowledge of chaos theory, we need to explore exactly what the traditional definition of chaos is. Traditionally, chaos is KK's hair. That is to say, a state of total disorderness and randomness. However, chaos theory presents the shocking precept that out of that randomness, disorder, there exists a very, very intricate order. Now, how does that come about? Now, let's go back. What exactly is this chaos theory that we're speaking of? Let's define it formally. Now, chaos theory is the study of complex systems that are highly sensitive to small changes in initial conditions. Pay attention to that butterfly. It's really important. So now, it all began with this man. Actually, it didn't begin with this man, but the man before him died during World War I, so we'll not talk about him much. His name is Edward Lorenz, and he was a professor at MIT. Now, Edward Lorenz was a meteorologist. That means that he studied the weather, and he came up with this system of 12 differential equations, which I had chosen to exclude because I didn't understand them much myself. But he came up with these 12 differential equations that model different variables in the weather, such as wind speed and pressure and temperature. And over time, he was able to come up with this graph. Now, this graph is particularly important because there was a day that Edward Lorenz wanted to run the sequence on the bottom over again because he wanted to see a particular pattern in the middle. He thought it was particularly interesting, wanted to see how it was going to work out again. But Edward Lorenz, like many academics, as I can tell you many of my classmates are, was quite lazy. So he chose, instead of running the pattern through from the beginning, he decided to start through at the middle. So he took his computer printout and he entered the values again there, but he was completely shocked because the end results were wildly different. So that begs the question, how can something that starts out so similar, because it was the same results that he had picked up from the computer, end up, look at it again, so completely differently? So let's revisit the definition of chaos theory. So chaos theory is the study of complex systems that are highly sensitive to small changes in initial conditions. So now, Edward Lorenz's computer recorded digits to 6 decimal places. However, his printout only recorded digits to 3 decimal places. So, the 1,000th, the 10,000th, the 100,000th, and the millionth digit were omitted. Now, if you've done physics before, I'm pretty sure that if you get 3 significant figures as your calculations, you consider yourself very lucky. Is that not true? However, because of a small variation of just the 3 smallest figures, there was such a wild difference in the outcome. And this is what has led to the coining of the famous term, the butterfly effect. And this is how all of you have changed the weather. So if there's a hurricane in China next month, it may be your fault. Over the course of time, in a complex system, a small change in the initial conditions can lead to massive changes in the outcome. So a single butterfly flapping its wings corresponding to, again, the 10,000, the 100,000, and the millionth of a decimal place can lead to a vast change in it. So a hurricane that would have happened in a month, your fault again, may not have happened, or a hurricane that would not have happened would have happened. So the outcome changes because of a change in the initial conditions of the system. And then came Edward May. Now, Edward May was a mathematician, and what was interesting about him was that he was a population biologist. And he wanted to investigate population using that relationship. And it's a quadratic relationship. So what he did was that he kept this constant, this year's population, and he kept the next year's population, 1 minus that constant. What he varied was R, the rate of population growth. What you would expect was that after a while, if R was high, it would come to settle at a high rate, and if R was low, it would come to settle at a low rate. However, what he ended up with was this. In the top left corner, you should get the expected. However, that's not what you expected now, was it? Not at all. But let's forget about him for a second. We're going to come back to him. It's important to pay attention to him, but we're going to come back to him. And let's move on to Benoit Mandelbrot. Now, what Benoit Mandelbrot did, note the mad hair. Maybe it has something to do with math, people with bad hair. But Benoit Mandelbrot, what he did was that he took cotton prices over 100 years and he analyzed them. And what he found was actually quite astounding. He found order, but not in the sense that you would come to think of order. He found order within order, within order. Again, it wasn't order in the traditional sense. It was order in the sense of scale. So if you took something and you blew it up, you would find the exact same thing that you started with. And what was really astounding was that the fluctuations in prices over two world wars and the Great Depression was exactly the same over years, as it was over decades, as it was over months, as it was over days, as it was over weeks. So the fluctuation in 7 days would be the exact same as the fluctuation over a month, the exact same as fluctuation over a year, the exact same as fluctuation over a decade. Let me repeat that. The fluctuations over a day would be the same as the fluctuations over a week, the same as fluctuations over a month, the same as fluctuations over a year, and the same as fluctuations over a decade. Order within order within order. So let's look back at this again. Edward May found exactly similar results, because even in the periods where there's total blackness, because as he increased the value of R, the value of the population would jump between different points. So first it would jump between 2 points, then it would jump between 4 points, and then 16 points, and then 32 points, and then you couldn't even tell what point it was going to land on anymore. However, if you zoomed into the white areas, you would find that the initial was repeated over and over again. And then there was a man called Mitchell Feigenbaum who discovered this principle called universality. And universality states that if you multiply or if you blow up a fractal 4.669 times, you will end up with an exact replica of the original. So in a system that is completely random, there exists order, but not in the way that you would expect it to be. It exists on an order of scale. So now there's a particular name for these kinds of objects, and they're called fractal. And what's really important about a fractal is that it has that dimension. But let's forget about that for a moment. It's not important, is it? So now, the dimension of the object is not equal to the dimension of the space that it occupies. Take a moment to take that in, because it has some really, really important ramifications. For example, that means that I can contain infinite length within finite space. But we'll come back to that in a minute. Let's move on. So fractals display two things. The first is self-similarity, and the second thing that fractals display is detail at end magnification. So no matter how much I blow a fractal up, I'll always find something, and at some point I'll find something that looks exactly like the original. Maybe not exactly, but to some degree like the original. So now let's look at how fractals are generated. Iterative function systems. I take a simple rule and I repeat it over and over again. And I'm pretty sure that many of you have encountered this object. It's called the Cobb curve. So I take an equilateral triangle, I trisect it at the edges, I draw another set of equilateral triangles. Repeat, 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 At this point, in a computer screen, it's not much use going any further because you will not be able to see this. But if I were to continue to infinity, eventually, that curve will be infinitely long. And any 2 points on it will be infinitely distant. How can you contain infinite length within finite space? Does that really make sense? Is that intuitive? Well, what's really mind-blowing about this is, again, the fractional dimension. Remember that log equation that I showed you? Well, the dimension of this is not really 2, although it looks like a 2-dimensional object. It's not 1 either, because it's better of a covering area than the line. So it makes sense that it's infinitely long. It's infinitely long. However, it's not as good as taking up space as a regular 2-dimensional object. Sorry? Such as a circle or a square. So, actually, the dimension of this is something around 1.2. I forget the figures, but I will forward my paper to you and you can read up on that. So, if you continue this, eventually, like I said, any 2 points in it will be infinitely distant from each other. And let's say we change the rules. Let's say we use color for every single iteration. You could eventually end up with something like this. And that exists in many forms of art from many different cultures, say Indian art. You find this. Fractals are actually very, very pervasive, and chaos theory is very, very pervasive because there are few things that it can be applied to. I mean, think about it. Anywhere there's a complex system, and anywhere a small change in initial conditions will lead to a great change in the end, you can apply this. And let's move on to strange attractors. Now, strange attractors have a funny name because the man who named them was funny. But let's not talk about him. What they do, what a strange attractor is a system in which there's an oscillation that repeats itself forever. It never comes to rest, but it never repeats itself. Again, a system that is an oscillation forever, but will never repeat itself. And that strange attractor represents the owl's eyes, right there, represent the foci of the strange attractor. So those are the points that the object that is in oscillation will always be attracted to. So now this that you see on the screen is actually a representation of a water wheel, and it was done by the man called Edward Lawrence. And what he did was that he took 3 differential equations, although at the time he didn't actually know that they represented a water wheel. He just did 3 differential equations because 3 is easier than 12. So he took 3 differential equations and he paired them down until they were not very realistic anymore. And he drew this. So now this in the 3-dimensional plane represents an oscillation around those 2 foci that will continually oscillate but will never intersect itself at any point. Were to look at this from the x-axis or from the y-axis or from the z-axis, at no point will any point in that curve repeat itself. And why it seems completely random is that if you're looking at it without tracing out its entire trajectory, it would seem like, where exactly is this thing going? But if you were able to trace out the trajectory of the entire thing, you would see that there's actually a very, very beautiful order that lies at the center of it. And then a very good example of a strange attractor in the human body is your heart. Now stand up again. I want you all to start jogging on the spot. Jog, 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 quickly. The faster you do it, the faster we can all sit down. Go on, go on, go on, go on. Stop. You may sit. Now, if you actually jog fast enough, your heart rate would have changed. And now the heart is a strange attractor because it's a system that oscillates forever. Because if it wasn't oscillating, you'd be dead. And it doesn't repeat itself because at different times, the different heart rates. And so this, again, shows the pervasiveness of chaos theory because it shows up in the strangest of places. But let's leave that for a second and let's move on. So Lindenmayer systems. Lindenmayer systems are systems by which a simple rule, again, is repeated over and over again. And it shows up in things such as blood vessels or in the nervous system, or the best example that I can give is trees. You take a line and you repeat it You break it off at the middle, and you repeat the pattern over and over again until you end up with what is a pretty realistic depiction of a tree. And where this may be applied is, say, computer graphics. You know, has anyone ever seen the Flintstones? Have you seen a car chase scene in Flintstones? What happens with the background? It's the same thing, just revolving over and over again, and they're running. So you keep seeing the same mountain over and over again. But if you've seen more modern CGI, you see that patterns are not repeated. Never. And whose fault is that? I think you should blame it on the fractal. Because the fractal will take a simple role and repeat it, but repeat it so much to the extent that the complexity makes everything different. So it's still the same simple role. It's just a simple role that you're repeating over and over again, cutting a triangle in half. But the complexity that results from that simple role is mind-blowing. But let's move on. And let's talk about escape time fractals. Now, an escape time fractal is usually done on a complex plane and it represents the amount of time it will take for a point on the complex plane to tend to infinity. And in my opinion, what is the most beautiful fractal is this, and it's called the Mandelbrot set. So now, what's mind-blowing about the Mandelbrot set? Sorry, I'll take a breath because this thing just blows me. So the Mandelbrot set is really, really interesting because the points that lie inside of it will not tend to infinity when you use the recurrence relation Zn equals Zn plus 1 equals Zn squared plus C, where C is any arbitrary constant and Z naught starts at 0. But the points at the boundary are what makes this fractal interesting. Because as you zoom into it, you find that at no point does the boundary simplify into simple things. There is no defined boundary on this. The points in the boundary do not exactly lie inside of it or outside of it. And as you zoom in, you find that the entire set is actually repeated in smaller scales. Again. And there the set shows up again. And you know, this set is so pervasive that it might even show up on the top of your cappuccino. When you make a cup of coffee from your dispensing machine, look at the pattern that the foam forms. That may be the Mandelbrot set. That is just how pervasive this is. Again, look at the entire set. Breathe it in. Breathe it out. And applications of chaos theory. Well, I couldn't come up with a finite list because really there's nothing that, in my opinion, you can apply it to. From mating selection to the way people get food in the dining hall. But what I think are two really, really important applications to look at are first, music. So how does chaos theory apply to music, you might ask me? Well, using the Oladimeji system, it's able to create, although it's not the most pleasing music to the ear, fractal music. And how does this work? First, we all know that the scale, sorry, I'm not going to sing it up, forget that. But the scale repeats itself, it's scaling. If you take it an octave high, it's an exact replica of the original. An octave high, it's an exact replica of the original, but on a greater frequency. So, therefore, by the definition that I have given you of the fractal, the scale is what? The scale is sorry? The scale is, do we want to stand up again? The scale is fractal. And using different methods of iteration, we can come up with fractal music. But I don't have much time left in my presentation, so I'll show you this pretty picture, and we can talk about art. And throughout the entire presentation, I'm pretty sure that you've seen examples of fractals and how parts of the Mandelbrot set have actually shown up in lots of postmodern art. The Mandelbrot set in itself has influenced a generation of artists. And personally, I think that if you do go to university and you leave without studying at least some aspect of chaos theory, you would have deprived yourself of a lot of things. So, questions, anyone? What's up?
So if I understand well what you're saying, it's just like there is no disorder. It's just because you do not see where the pattern starts, and if you see something, you might see it as disorder. Like in any disorder, there is order. So what you're saying is that disorder doesn't exist. Is that true?
I'm not saying that disorder does not exist, because chaos theory is still a theory because it hasn't been shown to exist in every single field. But I'm saying that for many fields, it is possible that what seems to be random is not random at all, but is actually determined by nonlinear deterministic factors. Say, a second order unsolvable differential equation. Harry?
My question is, you said something about the rate of heart not being the same at two exact moments ever. So does that mean that there are no two moments where you feel exactly the same?
I think Marie will answer you that. But it's not that you don't feel exactly the same, it's that the instruments that we use are a bit blunt to measure heartbeat. For example, getting, like I said before, 3 decimal places as a reading is actually a very, very, very great achievement as a scientist. So what I'm saying is if we could get infinitely fine measuring materials, you would find that the heartbeat does not actually ever replicate itself perfectly.
All right, we're going to have to stop there, but you can find Dimeji afterwards. Guys, let's give Dimeji another round of applause.